Hello everyone. Fortunately or unfortunately, today's class we will go online. So today's topic is about the matrix analysis of grading. Yeah, since we have learned about the transmission and scattering matrix last week, and we tell you or we tried to analysis the interface and the Fabry-Perot echelon with the scattering matrix and applied it to anti-reflection coating and the passive region. Now we are going to further use the same methodology to analyze the periodic structure, which is usually known as grating or DBR. Okay, this is the outline. So in order to treat the mathematical property of a multiplication of identical or periodic transmission matrix, we need to introduce its eigenvalue and eigenvector. Then we will tell you what is the Bragg condition for alternating films. Then it will be the general form or even it's not in the Bragg condition, we can still analyze its its reflectivity with arbitrary periodic structure. Then we will tell you what does the spectrum under of a perfectly tuned DBR with different wavelengths. The response with non-Bragg condition is called detune. So we will discuss the detuning of a distributed Bragg mirror. All right, so we discussed that what the DBR is. DBR, it means distributed Bragg reflectors. It is trying to deposit the two dielectric with different refract index, and if the thickness and the thickness well chosen, we can build up the reflectivity to a near one value. Grating is usually it's basically the same thing. Only the difference is that while in grating the refract index difference is usually smaller, and its purpose is usually not to build up a reflectivity to a very high value. It's usually used for wavelength selection. And we will have a more detailed discuss in next week for the grating. Okay, so now we take quick review of the transmission matrix. While we are seeing a system with power flow in and flow out, we might try to put the same for the power with the same direction with the same number. For example, we can assume okay, I can have some mark. We can assume all the power floating at the right direction with A, and the power flowing in the left toward left direction as B. So, and for each port, we have put the number in the subscript. So we can write down the relation between the port left and the port right as a vector of A1, B1 as its transmission matrix, and times the vector from the other side, A2 and the B2. So what if a system, if this is called a reciprocal means the physical phenomena seen from the port 1 and the port 2 should be equivalent. So in the point of scattering matrix, that means it should be a symmetric matrix, because I and J should be invariant to this system. So Sij should be Sji. But in the form of the transmission matrix, the mathematical deduction can be shown from last week. Its final conclusion is that the determinant of a reciprocal system should be has a unity determinant, or we can just say that its determinant should be 1. All right. Second, if the system is called lossless, that means the total output power should be equal to the input output power. So from the point of scattering matrix, we will get a moduli of each column of scattering matrix. For example, S11, S12, S21, and S22. Each column has a moduli. As a moduli means that we take the square of every term in the same column. S21 square should be equal to 1. Okay, so in the form of the transmission matrix, the equivalent mathematical description is that the T21 plus 1 should be equal to the T11, the T11, T12, T21, T22. Yeah, this value should be T11 square should be no, it's not equal. It should be the T21 square and the plus 1. Okay. Then we have two forming element of the transmission matrix of the arbitrary structure. One is the dielectric interface. So let's consider two dielectric with a different index. And the dielectric has a reflectix N1 here, and the other has a refract index N2 this side. And the power going from N1 to N2 is called A1, and the power leaving from N1 to N2 is A2. Similar for B2 and the B1, their power moving toward to the left direction. So according to the Fresnel equation, we have already said that we can find out the transmission elements of such a matrix could be written as something like this, which T is the transmissivity of the power from one to the other side, and the R is the reflectivity of the input power, like this one. So R12 means the reflectivity seen from number 1 and reflected by the median number 2, and the R21 is vice versa. And usually for a reciprocal system, the R12 should be minus R21, or it will be a pretty and weird interface. So with this criterion, we know that the T and this system will be the reciprocal will be reciprocal because its determinant will be equal to 1. And compare it with the result of the Fresnel equation, we can see that R12 can be written as the N1 plus N2 divides N1 minus N2. And for lossless case, yeah, this is true for lossless interface. It means that the T squared plus R squared will be 1. So in this case, T will be N1 plus N2 divides 2 square root N1 times N2. But this is not a must, because sometimes the interface might have some defect. So it's usually T squared plus R squared. In the most general case will be less equal or half to 1. Yeah, so the equal to 1 case is for the lossless interface or perfect interface. Okay, the transmission matrix element for homogeneous median is similar. And it only has, since we have already going into with detail last week, I'm not going to repeat that. the whole procedure. Anyway, the median will give you only a non-zero value at the diagonal entries, in the T11 or in the T22. And remember that the value will be plus for the T11 and the value be the T21. And the beta with a wave at the top can be separated into the beta in the real form and the I beta I as the imaginary form. Yeah, you can refine the detail from the class last week. Alright, so now here we start the point. So since we are trying to combine many systems for DBR, that will be alternating interface, median, interface, median, interface, median, So since we knew that the combination of two reciprocal system will still be reciprocal, because the determinant of a combined matrix will be the multiplication of the determinant one by one. That the determinant of T, which is T1 times T2, will equal to determine T1 and the determine T2 according to linear algebra. So since if each one is reciprocal, so this is 1 and this is 1, so the final answer is 1. So the combination of the reciprocal system will still be reciprocal. This is what we said last week. But today we have a more strong and implication about the reciprocal system. The eigenvalue and or the eigenvector. The eigenvalue of a reciprocal system will has two eigenvalue reciprocal to itself. Okay, that sounds pretty cool. That for example, if this T1 and the T2 has a eigenvector called A2, for example, A21, B21 match to lambda 1, and A22 or B22. The second two means only a specific number. It just means the second eigenvector, and its eigenvalue is lambda 2. For reciprocal system, lambda 1 and the lambda 2 is also reciprocal to each other, which means the multiplication of these two numbers will be equal to 1. Okay, so this is a very useful mathematical identity. We will show you why. And the proof is following. We just do the common linear algebra. Let the lambda as a lambda times I and put the other side. So it becomes a new matrix times an arbitrary vector to be 0. For non-trivial solution, it needed the determinant to be 0. So in this case, the determinant of the T11 minus lambda, T12, T21, T22 minus lambda should be 0. Okay, so after some mathematical deduction, and we need to use the fact that the T11, T22, and the T12, T2 is here. It's determinant. It need to be 1. So the lambda has a two solution. According to the fundamental algebra, we will find that we let the lambda plus with the plus in the middle, and the lambda minus means we are taking the minus term at the second one, and we directly multiply lambda plus and the lambda minus. We will find it as exactly 1. So we find the eigenvalue of a 2x2 reciprocal system should be has a two eigenvalue reciprocal to each other. Alright, since the value lambda 1 and the lambda 2 and reciprocal each other. So if one is lambda, then other one will be 1 inverse lambda. So there's an even more smarter way to write it in the exponential term. Yeah, we just write I say that if one is lambda and the other is lambda over 1. We can also let lambda to be exponential times c, and the 1 over lambda naturally will be exponential 1 and exponential times minus c. Yeah, either form will give you the conclusion that the multiplication yields to 1. Okay, so then we name such value c to be the discrete propagation constant. Yeah, although I don't know why they call this name. Anyway, we just remember that we transform the discrete. We can get the discrete propagation constant by taking the log of the eigenvalues. Then, with the corresponding eigenvalue, we have the corresponding eigenvector. You will be writing down like this way: T times eigenvector denoted plus, corresponding to the eigenvalue with exponential plus c. Similarly, the eigenvalue with minus c, we noted the eigenvector with minus as well. And if we expand it down like this way, we can write it down that the A divided by B, yeah, should be, it has two relations. The first is T12 divided by the echelon c. Ta over B will be T12 divided by exponential c minus T11. This part is from the equation here. Yeah, and similarly, we can also write down the extension, the second part, from the second equation here. Okay, so it's like this. Okay, then we can further see. The reason why we write it down in exponential term is that if we express the eigenvalue in such a formalism, then finding the eigenvalue of a repeating transmission matrix will be pretty simple. If the eigenvector has an eigenvalue of exponential c, then we times it m times. So it times m times, that means if AOBO is already an eigen, the value of that. So after it times it again, you will drop 1 exponential c out. So after timing the t for m times, it will drop out the exponential plus or minus m times c as the new eigenvalue. The eigenvector is the same, but the eigenvalue changes from an exponential c to exponential m times c. But the direction or the vector or the eigenvector is still invariant, only change the eigenvalue. Okay, let's take a short break.